Welcome back, everyone. This is number 5 of Chapter 10, Section 5 on elastic collisions. And this is a problem that a lot of students had difficulty with in class. And I can certainly understand that, but it's probably not for the reasons of the content it's hard. It's really just kind of tricky algebraically. But I'm going to walk through it, and hopefully that'll help you solve this kind of problem if you get it anytime in the future. So we have 2 balls. One is at rest. One is stationary. And I took the liberty of drawing these ahead of time here. Kind of like those cooking shows where they put something in the oven and they say, hey, look, this is already done, and they pull it out. So they prepare everything ahead of time, and so do I sometimes. So we have 1 rolling towards 2, which is at rest. Okay, so this is 2 is at rest right there. Why did I draw them this size? Well, I did cheat a little bit. I looked at the answer, and you know what? That looks like... That's funny. That is wrong. This right here should say 5/3 m. That's interesting. This is different from... Okay, well, tell you what. Change this. This should say 5/3. I just noticed that. I wonder why that's different. It should say 5/3, and I'll show you why in just a second. Okay, well, hopefully in a few seconds. 5/3 m. Basically, going back to my original point, I just cheated a little bit and looked at the and answer and said, okay, for drawing's sake, and your drawings don't have to be to scale, but just so the drawing does match the actual answer to the problem, I saw, okay, well, the mass of object 2 is bigger than the mass of object 1, so I'm going to just draw it bigger. That's the only reason I drew this one bigger than 1. Okay? But you could draw them the same size. The problem will work itself out. So the question is, what is the mass of the second ball? Well, we can write down what we do know. Let's write down what we do know. The mass of ball 1 is simply m. Okay, it's not a number. It's just a designation, m. And for those of you who like punching or plugging numbers in right away, this might be a little frustrating for you because we're dealing with simply variables and not actual numbers quite just yet. But this will get easier, so stick with me. The mass of 1 is m. The initial velocity of 1 is called VO. Now, if you might recall, VO is just another way of saying initial velocity. It could be VI or VO for original. Okay, but we're just going to call it that just because it's different from VI. Okay, the initial velocity of 1 is VO. And after it collides with ball number 2, so we have our collision, we're told that ball 1 rebounds. That is, it bounces back with a speed equal to 1/4 of its original speed. Okay, so we can say that the final velocity of object 1 equals 1/4 VO. But look, if it's rebounding, then what does that mean about the direction? Velocity is direction dependent. So if that's positive, then that means this direction right here has to be negative. So we need to put a negative in front of that 1/4 VO. It's bouncing back the opposite direction. Now, some of you may not like fractions, and you're certainly welcome to convert that into a decimal. That would be negative 0.25 VO, and that's perfectly fine. Okay, but the more important point is the fact that it is in fact negative. It's not positive. It's rebounding or changing direction and coming back. So we want to find out what the mass is of the second ball, and that we do not know. Mass 2 is the big question. Well, the good news about this problem is that mass 2 is initially at rest. The initial velocity of 2 equals 0 meters per second. I'm just going to write that right there. It's not really going to help us in terms of of our givens, but well, actually it will, because if you recall, why is it good that one of these objects is at rest initially? Because that means that our equations for solving final velocity of after an elastic collision, we can use the shorter versions. We don't have to use the longer versions. If you watch the podcast on problem 3, we use the longer versions. Here we can use the shorter versions of the equations because object 2 is initially at rest. So we can say, we have two possible equations to use to solve for this mass 2 right here. We can say that the final velocity of object 1 equals m1 minus m2 over m1 plus m2 times the initial velocity of object 1. Okay, that's one of our options. The other option we can say is, we can look at the other equation, the other final velocity equation. That is the final velocity of object 2 is equal to 2 times the mass of 1 times over m1 plus m2 times initial velocity of 1 as well. Okay, so both of these are potential candidates or potential equation candidates for solving for m2 right here. Okay, we're going to solve for this because both of these deal with initial velocity of 1, final velocity of 1. There's a final velocity of 2 in there, the masses and everything. But one of these will not work. Let's take a look at the second one first. Do we know this? Yes, we do. Well, we kind of do. We know that there's a certain quantity given to it. So we can say we know that. Do we know m1? Yes. Do we know m2? No, but that's okay because we're solving for that. Do we know the final velocity of 2? Well, we know the initial velocity of 2, but no, we don't know the final. So that means we have two unknowns, and we can't use that equation to solve for m2. So that one goes out the window, which means we're going to look at our other equation, our original one. Let me just erase that real quick and get it out of the way. There we go. Again, we're solving for m2, which also actually happens to be right here. So do you know vi of object 1? Yes. Do we have the mass of object 1? Yes, even though it's a variable. Final velocity of object 1? Yes, we do. So it should just be plug and chug, right? It is, except for the fact that, look, we have m2. We're solving for this, and it's in two places in this equation. If it were simply in one place, it would just be a matter of isolating it and solving for it. But this presents us with a little bit of an algebraic challenge. Really not a physics challenge at all, but an algebraic challenge. Can we solve for mass 2 right here? Can we get these together and then put the rest of the equation in terms of that and then plug and chug? And the answer is yes, we can. So this equation right here, a little bit messy, and we want to get the m2's by themselves. What's the first step? Well, what I would do is I would take this bottom denominator right here, okay, m1 plus m2, and that has to move as a unit because the m1 and m2 are added and that's in the parentheses, so that whole unit has to move somewhere all together. I'm going to take that and I'm going to multiply that by both sides because it's in the denominator. I'm going to bring it up next to the final velocity of object 1. Okay, so it's going to look like this. Final velocity of 1 times m1 plus m2 equals, and then we have all this as the numerator over here, equals initial velocity of object 1 times m1 minus m2. What do we do? Well, if nothing else, we at least made it linear, so there's no more fraction. Everything is in the same line. We still want to get those m2's together, but unfortunately they're added to these, or there's added or subtraction to these m1's, and then they're stuck inside these parentheses. How do we get the m2's out? Let's get them out by distributing the v's throughout on both sides. Okay, so it's going to look like this. V final, that's not final, V final 1 times m1 plus V final 1 times M2 equals V initial 1 times M1. Here's our minus sign, minus V initial of object 1 times M2. Again, this is just algebra. Really, the only hard part about this is the fact that this is just tedious. It's a matter of keeping your subscripts and everything straight. Okay, we're getting closer to being able to combine our M2s.